Hello everyone. In this video, we are going to talk about creep, which is the slow time-dependent deformations of the material under constant stress or under constant loading conditions, means F constant, usually at high temperatures. We will cover the three stages of creep, includes primary, secondary, and tertiary, and explain how temperature and this constant applied stress affect the rate of deformation or epsilon dot and the material's lifetime or rupture time or TR. If I want to explain briefly the difference between stress relaxations and creep, I should say that while creep focuses on how a material deforms under a constant load over a time at high temperature, a stress relaxation looks at how the stress in materials decreases over time when the strain or epsilon is held constant. Both phenomena are important in designing components that operate under high temperatures or long time loads such as turbine blades, boiler, pressure vessels. And finally, in this session, we will solve two example problems to see how engineers use creep data and the Larson-Miller parameter to predict rupture time and steady-state creep rates. Okay, creep is a time-dependent deformations of the material under a constant stress. As you see here, stress is constant, means stress not changed by time, constant, but the strain, as you see in this curve, completely changed by time. And this creep occurs at elevated temperatures for most metals when temperature is more than 0.4 times melting temperature in Kelvin. Okay. In creep tests, we measure strain versus time while maintaining constant stress and temperature. Even though the applied stress is below the yield strength or sigma is less than sigma y, materials can still deform slowly and eventually fail if the load is maintained long enough. As I told, we have three stages in creep that we call primary, secondary, and tertiary. Primary shows by red color, secondary as blue, and tertiary as green. The creep rate in primary decreases with time as a strain hardening occurs and the material adjusts to the applied stress. If I want to show how this rate decrease, you see the slope of this line as tangent decreases. So epsilon dot is d epsilon per dt. Here is the epsilon versus time, okay? For d epsilon, we need a slope of tangent lines, and you see in primary decreases. What about the steady state or secondary? Sometimes shown by SS, means abbreviation of steady state. The creep rate becomes constant. So here, epsilon dot is constant. As you see, it is completely linear. So the slope of lines tangent to this part have same slope. So this is the most important and longest stage of the creep. A balance exists between work hardening and recovery process. And finally, tertiary creep that shown by green color. The creep rate increase rapidly. If I want to show the, you see tangent to these curves, and you see the slope of these lines increases rapidly with time. So this happens due to necking, internal void formations, or grain boundary separations that leading to final fracture. The steady state creep rate or epsilon dot depends strongly on both temperatures and applied stress. So epsilon dot is functional. sigma that is constant, but the value is important, and the temperature. As temperature or stress increases, atoms can move more easily, so the creep rate increases. Okay, as you see, the slope of the lines may be in a steady state. For increasing temperature or sigma, we see that the slope increase. So if temperature increase, epsilon dot increase. If the value of sigma that is constant, but you compare, for example, 10 megapascal, 20 megapascal, they are constant during the creep test, but the value is important. So stress increase, epsilon dot or strain rate increase too. However, higher temperature and stress also reduce the rupture time. If I want to show the rupture time for the green one, T1, the rupture time for the blue one, T2, and the red curve is T3. So if sigma increase or T or temperature increase, TR or rupture time decreases as you see that T3 is less than T2 and less than T1. So higher temperatures means higher creep rate. Summarize that higher sigma, higher creep rate, higher T or sigma means shorter rupture time. Okay, a steady state creep rate. We told that we have 3 stages, and the steady state is one of the most important stages in creep process that the epsilon dot is constant. Dot constant for constant temperature or sigma. We know that it's function of them, but if T and sigma constant, epsilon dot should be constant too. So during the steady state creep, the strain rate remains constant for given temperature and stress. At this stage, 2 opposing process occurs. The first one, strain hardening. What's the meaning of strain hardening? Which resists deformation. And the second one is recovery, which allows dislocation to move and rearrange. These 2 effects balance out in a steady state and producing a nearly constant creep rate. If temperature or stress increases, dislocation motion become easier and the steady state creep rate increases and it completely makes sense. Okay, so I told that epsilon dot is function of sigma and temperature, and this function is this, K2 sigma to N E to minus QC RT. What is K2 is the material constant. For different material, we have different constants. Sigma is applied stress. That for creep test is creep constant. N is a stress exponent. That, for example, for metals and for metals, between 3 to 8 for metals. Okay. QC is activation energy for creep. So QC is activation energy. The unit is joule per mole, and is the energy needed for atoms or dislocation to move. R is the universal gas constant. R is 8.314 joule per mole per Kelvin. And T is the temperature that is Kelvin. And we have different curves for different materials. What's the meaning of these curves? Means by knowing the stress and by knowing the temperatures, you can measure epsilon dot or creep rate, or vice versa. We have epsilon dot, we have stress, we can approximately estimate the temperature. So if we have 2 of these epsilon, that is function of sigma and T. If we have 2 of them, we can estimate the third one. Okay, if you remembered from the previous slide, we say that epsilon dot is a constant sigma to n e to minus qc per RT. If the temperature is constant, so qc per RT be constant, okay? Multiply in A be another constant such as K. If we are looking for N and we want to find N, what should we do? So this constant is A e to minus Q C per RT. How we can find N? If we write Ln from both sides, should be Ln epsilon dot, should be Ln K plus Ln sigma to N. Ln sigma to N, and comes here, should be Ln epsilon dot Ln K plus N Ln sigma. Okay, if we have several data at constant temperature, so easy. We have epsilon dot and we have sigma, and we can find N. As you see here, for pure metals or solid solution alloys, N approximately between 3 to 8. For diffusion control creep, N approximately 1. For dislocations climb control creep, N between 4 to 6. And for grain boundary sliding, N between 2 to 3. Okay. Predictions of creep rupture lifetime. Time to rupture, or TR. It's not practical to run a creep test for many years. You know that it takes much time in laboratory. So engineers use mathematical models to predict long-term performance. The most common method uses the Larson-Miller parameter, M, which relate temperature time to rupture and applied stress. Okay, here we see that T is the temperature, C is a constant, normally considered at 20, logarithmic of TR, that is rupture time, and M is function of applied stress. If you remember, I told that for rupture time is function of sigma and T. We see the effect of T completely here, but we don't see the effect of sigma here. Sigma play a role in M, and you see in previous slides that how by having the sigma we have different M, that the name of M is Larson-Miller parameter. So as I told, it is not practical to run creep tests for a long time, many years in lab. So we have to use the mathematical model to predict the rupture time. The most common method is Larson-Miller parameter, which relates the temperatures, time to ruptures, and apply the stress to each other. And it allows us to estimate how long a material can withstand certain stress or sigma and temperatures conditions before the fail. Here is the first example. Estimate the rupture time, or TR, for S590 iron at temperature 800 centigrade, and sigma, or applied stress, is 20,000 psi. Okay. First, temperatures convert to Kelvin should be 1073 Kelvin. Use the equation that we have for Larson-Miller. T times C, that C is the constant 20, plus logarithmic of TR rupture time, equals M, that is the Larson-Miller parameters. We have T, we have C. We are looking to TR, but what is M? M is a function of applied stress, 20,000 psi. Come here and read the M. M should be 24 times 10 to 3. Substitute here and find TR as 233 hours. Okay, mathematically, the unit of this M should be Kelvin, but particularly in graphs and charts, it is often labeled as Kelvin hours, or KH. To emphasize that these parameters combine both temperature and time effects. The second problem. For this example, we have a cylindrical samples 7.5 millimeter in diameter, so D is 7.5 millimeter, and the material is S590 alloy. It is to be exposed to tensile load, so force is 9,000 newtons. At approximately what temperatures will the steady state creep be 10 to minus, so epsilon dot should be 10 to minus 2 per hour. Okay. First, we need to find the stress. Then this stress is constant, but we should find that it should be F per cross-section area. Cross-section area pi r squared or d per 2 squared. We substitute that and we find sigma equals 204 megapascal. Okay, we find sigma, and these charts or a graph or something only is for S590. So for different material, you should use the different graphs, yeah? For 204, we approximately consider 200, and epsilon dot was 10 to minus 2. 10 to minus 2. Okay, so temperatures approximately be 815. To summarize, creep is critical factor in high temperatures applications and occurs in three stages: primary, steady state, and tertiary. The steady state creep rate increases with both temperatures and applied stress. And the Larson-Miller parameters allow us to predict long-term ruptures without waiting years for experimental data because it takes much time. In the example we solved, we estimate the rupture time for S590 iron and determine the temperature need for a specific steady state creep rate. These tools helps engineers design safer, more reliable components. I hope this video helps you understand creep better. If you found it is useful, please subscribe for more lessons on mechanical property and fracture mechanics, and feel free to leave any questions in the comments. I will be happy to answer all of them. Thank you and bye-bye.